In this section, we're going to talk about volumes of solids. And this is really an interesting thing that is related to integration. It's really fascinating how we can find the volumes now of different items, either revolving around an axis or a line or just different shapes in general. It's just really cool. So what we're going to look at is volumes of solids. Almost any solid you can think of, as long as there's some sort of function that goes with it. And the volume of a solid of a known integrable cross-section of area. Okay, we'll call that AX. So in other words, we need to know how to find the area of some shape. From x equals a to b is the integral of this function a from a to b. It looks like this. Okay, so if we integrate the area, okay, the area times the change in height, all right, then when you have area times height, you have volume. Okay, and so the first problem we're going to look at deals with a pyramid shape, and so it's kind of hard to draw 3D-ish, but basically what we're looking at is some sort of pyramid guy that creates a square, and it comes back to the origin, something like this. Okay, and what we're wanting to do is we're wanting to find the volume of this whole shape in here. We want to find the volume of that whole shape. But how are we going to do it? We're going to find the area of the square that's dotted. We're going to find the area of that guy, and then we're going to look at an infinite number of little slices along the x-axis coming back. So we're going to take a little slice, 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 and we're going to do this. And when we integrate that with all those little heights and add them all up, we get the volume. Okay, so area equation times dx equals volume, especially when you integrate it. So some tips for finding volumes by doing this little slicing method is to find a formula for the area. Okay, sketch out what your graph might look like. Find the limits, so where are you starting and stopping, and then integrate it. And if you're one of my students, you have total permission now to use the calculator to help you. We did our test previously with integration. If you're not one of my students, then you will need to go ahead and show all your different steps. So let's look at one. A pyramid 3 meters high has congruent triangular sides and a square base that is 3 meters on each side. Each cross-section of the pyramid parallel to the base is a square. Find the volume of the pyramid. Now, this is going to be a little difficult to draw, and I'll try and draw it as best I can, but I am not a super great graphic 3D artist. So this would be the x-axis kind of coming at us. Here's the y-axis going straight up. And basically what we're looking at here is a situation where we've got this pyramid shape, and it told us it had square pieces. All right, so let me clean this up just a little bit here. Remember, that's x, and then so all these different corners come back to the origin. Okay, and what we're wanting to do is we're wanting to find the area of this part right here, this guy right here. What's the area of this square? Okay, and if we think about the area of this square, we are x units wide. Okay, we're x units here, we're x units here, we're x units here, we're x units here, and we're also to that point x units. Okay, so we've got these straight lines all coming off all over the place, and we're told that our pyramid is 3 meters high. So if this is 0, this right here where our last line is 3. So we know we're going to integrate from 0 to 3. Okay, and we know that we've got all these different little squares in here that we're trying to find the area of. Well, how do you find the area of a square? You do a side times a side, or x squared. And then we also need to multiply by the width of each square, so that would be dx. Okay. And how do I know that each one of these is x units in length? Because I know that I've got congruent triangular sides and a square base. It's 3 meters on each side. So if my base comes down here to 3, this guy's 3, this guy's 3, this guy's 3, this guy's 3. So everything is all in relation for this particular setup. So integrate this guy. We're going to integrate him. He's going to be x cubed over 3, evaluated from 0 to 3, which will give us stop minus start, 3 squared, 3 cubed divided by 3, minus 0 cubed divided by 3. And when you punch that in, you're going to wind up with 27 over 3 minus 0, or 9, and then 9 what? 9 meters cubed. Now, this first guy looks really complicated. We weren't necessarily given a specific equation to work with, but use your brain here. I mean, we've got a distance from 0, and everything's in relation. So that's how we know that we have x's all over the place. If we just pick some random spot, we are x units from the origin, and the sides are x units long. Okay. If we're given a function, that makes our job just a little bit easier. All right. And we'll see several examples of this coming up. But there you go. Here's my area equation. Here's my height. I got to have that. I know what I integrate from, what I integrate to. Okay, this will be a little bit easier, I think, to see, because now we're dealing with some actual functions. But what if we have a circular cross-section? What if we take some graph, some random graph, and we rotate it around the x-axis? So what we're going to do is we're going to take our x and y axis, we're going to give it some curvy thing, and then we rotate the curvy thing around the x-axis. And what it does is it will actually give us a 3-dimensional shape with volume. And if we pick some point on the curve, it's going to rotate all the way around and make a circle. So if we need area times the height, okay, we're going to still stick with that whole area times the height. So we're still sticking with this guy right here. How do you find the area of a circle? And the area of a circle is equal to pi r squared. And when you're dealing with volume and you're dealing with all kinds of cool functions, the radius is the distance from the x-axis, or the point of rotation, to your curve. That's your r value. So whatever our function is will be equal to our r in most cases. Now, if you rotate around a specific line or something else, we'll have to do a little bit more math. But if we rotate around the x-axis, our function is our radius. So we would look at the function squared, which is this part, times pi. And then for the volume, we would add times the dx. Remember, if we were to look at this from the side, straight on from the side, and we've got this fun shape here, if I integrate from here to here, and I want the volume, then I add up this volume plus this volume plus this volume plus this volume, and that's where the dx comes to play. It takes care of the height. And if I add that enough, I can get to my the volume of my shape. All right, so I'm going to delete these guys real quick, and then we're going to look at our problem. All right, so what I've got is the region between the graph of f of x equals 2 plus x cosine x and the x-axis over the interval -2 to 2. And this is going to be kind of fun. If we do this by hand, we're going to have to use integration by parts, because there's no way to handle x cosine x. If you're one of my kids, and the way I'm going to solve it on this particular video is I'm going to use my calculator. So what we've got is this graph. Hold on one second. Brilliant idea to add our graph. So here it is. We want to find the volume of the solid from 2 to 2, from -2 to 2. So we start here at -2. We go over here to +2. And we rotate this around the x-axis. So, you know, if we rotate the shape around the x-axis, we'll get a shape that looks kind of like a vase. So if you can imagine this guy, you know, doing something along the lines of, and I'll try and sketch it out really well. something along the lines of this. Okay. And notice we would integrate all the way down to these places. And so we're going to get a circle shape. We're going to get a circle shape right here. We're going to get a circle shape right here. Okay. And so what's the area of this circle? The area of this circle is this guy right there, 2 plus x cosine x. So the integral on this particular one, and they give us the setup, goes from -2 to 2. And it's going to be pi times the whole thing, right? Times 2 plus x cosine x squared, because that's the radius, dx. Okay? Punch this into your calculator now. It's really easy to do. It's not hard. And when you do that, when you punch it in, I get 52.43 units cubed. Now, make sure that on your calculator for your mode that you are in radian mode. If you're in degree mode, then this will come up a really wacky, weird number. Okay? So don't let this be hard. Anytime you rotate something around a fixed point, something around that fixed point, you get a circle every time. And so the area of the circle is pi r squared. The function is the radius in this case. And life is nice, okay? And we're going to pause it here before we look at the bottom equation, because this guy is actually going to involve a washer. So hold on, we'll see what it looks like. All right, we want to look at the region now in the first quadrant enclosed by the y-axis and the graph of y equals x cosine x and y equals, or just y equals cosine x and y equals sine x. We want to revolve that around the x-axis to form a solid. So I've got down here a graph of what that looks like in the first quadrant. And we're looking at now, well, that shade, that color is really close. We want to look at, let's see here. We want to look at, not banana, tangerine. If we take this part in here and rotate it around the x-axis, notice that we're going to have a space in the middle. So, you know, we would have our blue line would look like this. Our green line would look like this. And notice when we rotate that around, what's going to end up with in there is some space in the middle where we have nothing. Okay? And then we've got this outer ring where we have everything. And notice the shape we get on this is a washer. We're hollow here in the middle. We're hollow. There's nothing in this space. We're filled in on the edges because that's the area that's in between those two curves. And we want to find the volume of this shape. Now, this is a hard shape to visualize. It's hard to draw. It's hard to get a good look at. But you can find online, if you type in 3D washer, you can get some good looks at what this would look like. So what we need to do is figure out the outer radius, that's the big R, and the inner radius, that's the little r. And we're going to take the outer radius squared minus the inner radius squared times pi. Okay, now that gets us the area of the cross section. Please know that this does not equal this. Okay, if you attempt a washer problem this way, you are going to be doomed from the start. Okay, notice that it's big R squared minus little r squared inside the parentheses. Okay, so what we have to do is figure out where these two guys cross. We need this point of intersection right here, okay, which should be the same exact point. If you remember your first quadrant trig, we know that this is going to be the point pi over 4 because that's where the x and y coordinates are the same for sine and cosine. If you don't remember, you can use your calculator to help you out, or you can use a trigonometric sheet or find a unit circle with all the labels on it. So what we want to know is we want to know the area from 0 to pi over 4. So that's how our integral will set up from 0 to pi over 4. Okay. Again, pi can go on the outside because it's a constant, so we'll put pi out here. And then times the outer radius. Well, what's my upper function here in blue? Which of those two trig functions goes through the point 1 at 0? And that's going to be cosine. So I have cosine squared x minus the one that goes through 0, this lighter green one. It's going to be sine squared x dx. Okay, and that's the setup for this guy. Now, if you're in my class, you totally have permission to punch this into your calculator and get a decimal answer. I've already graded you on integration. If you're not in my class and you need to integrate this, integrating this from here is pretty difficult. So what we want to do is we want to use a trigonometric identity, which says that cosine squared x minus sine squared x is equal to the cosine of 2x. So you've seen this trigonometric identity somewhere before. Now, you may or may not remember this, but if we let u equal 2x, du would be equal to 2 dx. So 1/2 du equals dx. We would have to make a u substitution. And when we do that, we're going to have a substitution that's going to look like pi from 0 to pi over 4 of 1/2 cosine u du. Okay, so when you integrate this and substitute back in, you're going to wind up with pi over 2, okay, times the sine of 2u, or sine of 2x, and we're going to evaluate that from 0 to pi over 4. Okay. So substitute your 0 and your stop minus your start. You substitute all of this in. I'm starting to get squeezed on room. So I'm going to have pi over 2 times the sine of 2 times pi over 4. That's pi over 2. 2 times, let's see here, 2 times pi over 4. Okay, the 2 and the 4 cancel. That leaves me pi over 2. Minus pi over 2 times the sine of 0. Okay, so the sine at pi over 2 is 1. So that's going to be pi over 2 times 1 minus pi over 2 times the sine of 0 is 0. And so for this particular guy, we're going to get pi over 2 units cubed. All right, and that's using your washers. So washers are going to be an outer ring minus an inner ring. Okay, the volume of a circular cross section is just going to be the area of the circle, pi r squared, integrated from our start to our stop. All right, so they're very, very closely related. Don't let these be super challenging, but sometimes you're going to have to pay attention to figure out which graph is the larger radius and which graph is the smaller radius. Okay, the final way that we can find different volumes using integration is by finding the volume of a cylindrical shell. And these can be just a little bit tricky because it requires your brain to think a little bit differently than we would normally think. So I'm going to show you this, and it's just going to take some practice to get comfortable with the shell method, okay? And a lot of times, instead of using a shell method, you could use a washer method. But sometimes it's easier to use the shell method as well. So I'm going to show you how to attack this guy, and then you can practice it on your own. And just like with some of the previous slides on this, with my kids, you've shown me how to do integration already. So you can use your calculator. With other kids that are watching this, and your teachers may be not quite as strict, or if you're in an AP calculus class, you'll need to work this out by hand. Okay, so a cylindrical shell, basically what we're going to do is we're going to rotate this graph that we've got, y equals square root of x and x equals 4. We're going to rotate this around the x-axis, okay? And so when we do that, though, we're not thinking of a circular piece. We're thinking now about a shell, which is a little bit different. So notice, if we rotate around the x-axis, we have two from A to B. From in this case, A is going to equal 0, B is going to equal 4. Okay, so we're going to go from A to B. But the shell radius and the shell height now are going to be in terms of y. We're going to be in terms of y. Okay. And so, you know what? And there's the first mistake that you're going to make. Since everything's in terms of y, we have to look at what's going on in relation to the y-axis. So if we rotate around x, here's our a and here's our b. All right, so in this case, a is 0, b will be 2. And then we have to get our equations to say not y equals, but x equals, okay? So if I have y equals the square root of x, if I solve this for x, I'm going to square both sides. And that's going to get me y squared equals x, okay? So here we go. We're going to start setting up our integral. Our integral is going to go from 0 to 2 on the y-axis because we're rotating around x. It's a little bit different. And then we're going to have 2 pi in there. Well, because 2 pi is a constant, I can put it in the front. So I'll just move this guy over a little bit. I can put my 2 pi here. And then on the inside, I need to have my shell radius. And then I need to have my shell height. Okay, so these are two kind of different things. So remember, everything now is kind of in relation on the y-axis. So we're rotating around on the x-axis. Wow, that's really good. And so my shell radius now is actually going to be this part right here. All right, this guy right here is the shell radius. I'll use a different color. Here's my radius, and notice that my radius is changing every time. Okay, there's my radius, there's my radius, there's my radius. What is my radius? That's going to be y squared. Okay, whoopsie here. We're talking about radiuses, and remember, we're talking with the y-axis, so these r's are all correct. But what do those r's represent? They represent values of y. Okay, they represent values of y. And so the radius on this guy is how far in y coordinates we are off of the x-axis. Okay, so our shell radius is going to be y. Our shell height then is going to be where we stop, which is this 4 right here. We're stopping here at 4 on the x-axis, right? But we don't need any of, like if I went ahead and from this B, if I filled this in, we don't need any of this space right here. So our shell height, or how tall we are off of the y-axis, is going to be this way. This is our height, okay? And our height is going to be 4 minus whatever that function in terms of y is. So in this case, it's going to be 4 minus y squared. And always put parentheses, because if this was like y squared plus 2 or y squared minus 7 or y squared plus y plus whatever, then we want to subtract that whole function, okay? Which in this case, it's not too bad. It's just 4 minus y squared. So my shell height then is going to be 4 minus y squared. And then our change in our thickness of our shell is going to be the dy. Okay? So one thing that you can do that will help give you a good visual, because I'm a terrible 3D drawer, is you can look, go to Google and just type in calculus shell method. Okay, and it'll give you a much better kind of 3D-ish view with fancy software and all kinds of stuff. And you can just see a couple pictures to see exactly what the shell is. But it truly is giving us, instead of a washer, like a washer that you would build stuff with, it's giving us more of a shell, like a peanut butter jar that we're using to determine the different ways to find volumes. Okay, so back to integrating this guy. It's not too difficult to finish it from here if you're one of my kids. Punch it in your calculator. If not, remember, we're actually going to integrate 4y minus y cubed, and so this would be 2 pi times 4y squared over 2 minus y to the 4th over 3. and we're going to evaluate that from 0 to 2. Now, the zeros, when we put zeros in, since we got zeros in all the terms, y's in all the terms, that will just cancel out and become 0. So we really just need to work with the 2. So that's going to be 2 times pi times 4 times 2 squared divided by 2 minus 2 to the 4th divided by 3. So 16 divided by 2 is 8. So we have 8 minus 16 thirds times 2 pi, which is going to be 24 thirds. So 24 minus 16 is 8. 24 minus 16 is 8 thirds times 2 pi, which is 16 pi over 3 units cubed. All right. Is that right? Let me make sure I did all my math right here. I feel like something's not right. 4 times 4 is 16 divided by 2 is 8. 2 to the 4th is 16 divided by 3. So 24 over 3 minus 16 over 3 is 8. Oh, there it is right there. There it is. I found it. This should be a 4. That makes some changes. There we go. There we go. My calculus senses were tingling. So let's fix that just real super quick. So this is going to be over 4. There we go. All right, so this is going to be 8 minus 2 times, let's see, 16 divided by 4. 8 minus 4. Gee whiz. 8 minus 4 times 2 pi. That's going to be 4 times 2 pi, which is 8 pi units cubed. There we go. There we go. There's the shell method for you. And it's a little bit different. It takes some practice, but it's one that you can do. So depending on which way you rotate depends on the setup. Okay? Okay, here we go. One more quick example, because these cylindrical shells can be quite challenging in the way that they make us think. So we want to use shells to find the volume of the region revolved around the y-axis. Here's our boundaries. So that means that the region we're interested in is in here. So we want to find the region of this guy revolving around the y-axis. So if you'll go back to your previous slide and look, then what we're doing is we're going to integrate according to x. Okay, we're going to integrate according to x because we're revolving around y. It may be easier to see the shell with this one. So here's the height of my shell right here. Here's my shell height. Okay, from way up here to right here on this x, the line y equals x. My shell radius then is going to go from 0 out here to whatever value I need, okay? And so when I set this guy up, he's going to follow the same rules that we did on our previous problem. But this time, since we're going around the y-axis, okay, we're rotating this way around a y-axis, so like a Pringles can, okay? Then we're gonna find where this point of intersection is, and I use my graphing calculator to do this. You could set x equals 4 minus x squared and solve it out that way as well. So we're going to integrate from 0 to 1.562. We're going to have 2 pi in the front. We're going to have the shell radius, which is the x coordinate, okay, times the shell height. And the height on this one is just from that line from 4 minus x squared to x. But remember, we're not going past 4 either. It's like we've got this invisible line up here at 4, so we want to know all the area under here, but only that area under there. So when we set that guy up, we're going to have 4 minus x squared, which is this upper line, the reddish one, minus the line that we stop at, so the whole top minus bottom thing. So 4 minus x squared minus x. Now remember in the previous problem, we had a vertical line there, which allowed us to just put the number 4 in and subtract from that. So top function minus bottom function. And so it's going to look like this right here. And when we integrate, since we've got the 1.562 in, I would say go ahead and use your calculator on this one, because dealing with decimals, doing integration, there's lots of room to make a mistake. So we're going to have 4x minus x cubed minus x squared, and all of this is dx to represent our change, our small changes, but horizontally. Okay, so punch this into your calculator. It's not hard. And when I do that, I get 13.327 units cubed. Let me make sure. 14.327 units cubed. Okay, so there you go. There's another shell guy. Could we also find the same area using washers and revolving around the x-axis? Yes, we can, and that's what's so neat about shells and washers. You've got two ways to solve it. So some of you guys may look at this problem and go, man, I see the shells, it's not a problem. Some of you guys will look at this and go, I see washers. Hey, guess what? Not a problem. But follow the directions in your book, follow the directions on your exam. Whatever method they ask you to use, you'll want to do that. And sometimes it's easier to use one as opposed to the other. It just depends on the problem. All right, so there you go. More cylindrical shells. I think this is just really cool stuff.